The appearance of a years-long supernova explosion challenges scientists' current understanding of star formation and death, and work is underway to explain the bizarre phenomenon. Stars more than 8 times the mass of the Sun end their lives in fantastic explosions called supernovas. Supernovas that form from supermassive stars typically rise quickly to a peak brightness and then fade over the course of around 100 days as the shock wave loses energy. In contrast, the newly analyzed supernova IPTF-14HLS grew dimmer and brighter over the span of more than 2 years, according to a statement by Las Cumbres Observatory in Goleta, California, which tracked the object. Details of the discovery appeared on November 8 in the journal Nature. Supernova IPTF-14HLS was unremarkable when first detected by a partner telescope in San Diego on September. And the supernova looked like it was already fading, he said. The observatory was in the middle of a 7.5-year collaborative survey, so Arcavi focused on more promising objects. But in February 2015, Zhang Chuan Wang, a student working for Arcavi that winter, noticed the object had become brighter over the past 5 months. He showed me the data, Arcavi said, and he asked, "Is this normal?" And I said, "Absolutely not." "That is very strange. Supernovae don't do that," Arcavi said. At first, Arcavi thought it might be a local star in our galaxy, which would appear brighter because it was closer, he said. Many stars are also known to have variable brightness. But the light signature revealed that the object was indeed located in a small irregular galaxy about 500 million light-years from Earth. And the object only got weirder. After 100 days, the supernova looked just 30 days old. The supernova recently emerged from behind Earth's sun, and Arcavi said it's still bright after roughly 3 years. But at 1/100th of its peak brightness, the object appears to finally be fading out. Just to be clear, though, there is no existing model or theory that explains all of the observations we have, said Arcavi. This means that the event Arcavi has been observing, whatever it is, may actually be 60 years running. There's a 1 to 5% chance the two events are unrelated, but that would be even more surprising, said Arcavi. Astronomers have never observed unrelated supernova in the same place decades apart. "We are beyond the cutting edge of models," Arcavi said. "I'm not sure, and I don't think anyone else is sure, just what the hell is happening," astrophysicist Stanford Woosley at University of California, Santa Cruz told Space. With this formula, Albert Einstein demonstrated that matter and energy are fundamentally interchangeable. Stars burn by converting matter into energy, fusing lighter elements like hydrogen and helium into heavier elements, which build up in the star's core and also release energy. (8 billion degrees Fahrenheit). This energy-matter equivalence produces pairs of electrons and their antiparticle counterparts, positrons, Woosley said. The process robs the star of energy, and so the object shrinks. But as this happens, the temperature rises in the star's core. At 3 billion C, 5.4 billion F, oxygen fuses explosively, blowing off massive amounts of material and resetting the cycle. The star continues to fuse oxygen and the elements of greater masses up until iron, at which point the reaction fails to release enough energy to keep the star from collapsing in on itself. Eventually, a star like the one that gave rise to IPTF-14 HLS will collapse into a black hole without another explosion, said Woosley. This phenomenon, called a pulsation pair instability (PPI) supernova, could account for IPTF-14 HLS sustained luminosity as well as the object's varying brightness. However, the PPI model cannot account for the tremendous amount of energy IPTF-14 HLS has released. The first explosion of 2014 had more energy than the model predicts for all the explosions combined, said Arcavi. What's more, this phenomenon has yet to be verified observationally. Stars between 80 and 140 solar masses, which do this kind of thing, have to exist, said Woosley, and they have to die, and so, somewhere, this has to be going on. But no one has seen it yet, he said. An alternative explanation involves a star 20 to 30 times the mass of Earth's Sun. After a more conventional supernova, such a star could have condensed into a rapidly spinning neutron star, called a magnetar. A neutron star packs the mass of 1.5 suns into an object with a diameter about the size of New York City. A neutron star rotating at 1,000 times per second would have more energy than a supernova, according to Woosley. It would also generate a magnetic field 100 trillion to 1 quadrillion times the strength of Earth's field. As the star spun down over the course of several months, its incredible magnetic field could transfer the star's rotational energy into the remnants of the supernova that it formed from, releasing light, Woosley explained. "It's like there's a lighthouse down in the middle of the supernova," said Woolsey. But the magnetar explanation is not perfect either. It has trouble explaining the dips and peaks in IPTF-14HLS brightness, and the physics behind how such a phenomenon might work is still uncertain, said Woosley. As IPTF-14HLS sheds energy, Arcavi said he hopes to be able to see deeper into the object's structure. If it is a magnetar, then he expects to see X-rays, previously obscured by the supernova itself, beginning to break through, he said. Maybe by combining pulsation pair instability with a magnetar, you can start to explain the supernova, Arcavi said. The existence of IPTF-14HLS has far-reaching implications, the researchers said. At 500 million light-years away, the supernova is still relatively close to Earth, and the universe is practically the same today, in terms of composition and organization, as it was when this event occurred, according to Arcavi. If the event was a PPI supernova, it tells astronomers that stars more than 100 times the mass of the Sun, thought to be more prevalent in the early universe, are still forming today. The event also had far more hydrogen than researchers expected to see. The explosion in 1954 should have expelled nearly all of the star's hydrogen, said Arcavi. Astrophysicists will have to revisit their models of supernovas to understand how this can occur, he said. The finding has ramifications for the study of galaxies as well. The energy of the gravity that's keeping that galaxy together is about the same order of magnitude as the energy that was released in the supernova, Arcavi said. So, a few of these in a galaxy could actually unbind the entire galaxy. Arcavi and his team plan to continue monitoring IPTF-14HLS for at least 1 to 2 years. And a suite of international telescopes and observatories will join the effort. Swedish colleagues at the Nordic Optical Telescope in the Canary Islands will track the object as it continues to dim beyond what Arcavi's telescope array can detect. NASA's Swift spacecraft will look for X-ray emissions, while the Hubble Space Telescope is scheduled to image the location beginning in December, and others will follow, Arcavi said. That's what we live for, what astronomers love.